All right, so last class sort of gave us a glimpse into what we need to consider. So so we had a problem from the homework, and what it did is it gave us an integral that we weren't sure how to handle. So in particular, it was this integral. So what we were trying to do is we were trying to compute the length of the parabola y equals x squared. And the length of that particular curve is given exactly by this integral. And what we found is we weren't able, if you tried even, and I didn't ask you to do it, but even if you tried, you would find quite readily that it's a challenging integral. So our knowledge of integration so far can't help us. So what I mean by that is there's no sort of algebraic trick. There's no simple identity. There's no U substitution in an obvious way that's going to help you. So let's make that, fairly clear here. If I try to let the inside of the radical be equal to a new variable, say u, what you'll see is it doesn't work. So what this sort of leaves us with is a dilemma. And what I mean by the dilemma is the following. So in fact, we know very little about integration techniques. For example, let's look at something that might seem a little harmless, but isn't. What is the integral of the secant? What is the integral of sine cubed? And we can list many more. Let's list some other ones. What if we wanted to integrate x e to the x? What if we wanted to integrate e to the x sine x dx. What about the integral of the natural log? So the point I'm trying to emphasize is that if we are trying to think about our integration skills at this point in our calculus course, in the big picture, we know very little. And so what we want to do is we want to remedy that. We want to figure out a way to determine these integrals. And what we'd like to do, as we normally do in math, it's not just that we want to sort of know how to solve one of these in particular or another, but if possible, we would like to develop systematic sort of procedures that we can employ at different times when they seem relevant. Now, of course, one of the things to always keep in mind is if I ask you to compute one of these integrals, modern technology gives us a shortcut. There's apps for your cell phone, there's web pages that if you know how to ask them correctly, they will not only give you the integral that we're asking, but they'll also show you how to derive the formulas. And so what we'd like to do today is we'd like to talk about some of these sort of techniques of integration so that we can answer questions like I just posed above. So that's sort of where we're going to go right now. So our current goal is to develop more techniques of integration. So if you think about how you might develop some sort of technique, you might look to the relative of the integral. And what we learned in Calculus 1 is that the integral is very intimately related to a derivative. In fact, it's the reversal or the inverse operation of taking a derivative. And so what we spent time in Calc 1 trying to point out, and I've alluded to even in this course, is that all your basic differentiation rules have analogous sort of formulas in terms of integrals. The big one being the chain rule for computing derivatives can be thought of in terms of integrals, and that's what we called our change of variable or our use substitution formulas. So let's make sure that we take an important note of that. So in Calc 1, we develop I shouldn't say the. So let's be, yeah, I guess I could say the. So we develop the technique of U sub, which is really called a change of variable. And we did this by investigating the chain rule. And so what that suggests is maybe we should look at one of the other rules we haven't considered yet, most notably what if we investigate the product rule. So you'll recall the product rule says you have the derivative of f times g. We can write it in this prime notation as f prime times g plus f times g prime. Or you might want to write it in terms of d dx, where you might say this is df dx times g plus f times dg dx. So when I say investigate that, what I'm suggesting is let's look at this formula that we know and love from calculus and ask, what if we were to rewrite it not in the language of derivatives, but in the language of integrals? So let's do that. So here's how I'm going to do it. If I have my formula, which is f times g prime is equal to f prime times g plus f times g prime. So what I'd like to do is I would like to integrate both sides with respect to the variable. So that means I would have this and then I'll do each one of these pieces separately. And the key observation to sort of pick out is that on the left-hand side, the integral and the derivative undo each other. So what I mean by undo each other is the fundamental theorem of calculus says the left-hand side simplifies to just f times g. And on the right-hand side, we have two integrals. And so we can solve one for the other. So another way of writing this would be as follows. If I rearrange this equation, I can write one integral. I can say f times g prime dx is equal to f times g minus the integral of f prime times g dx. Which right now to you means nothing. It just looks like a scary formula. And we're going to tell you why it's actually, even though it looks intimidating and it looks, you know, more like hieroglyphics than anything, we're going to tell you why it's useful. Does anybody have a question so far? So this formula that I have written in blue has a name, and it's called the integration by parts formula. And it is very useful. And let's look at why it's useful. What can possibly make this scary thing useful? Well, if we flip back a page, let's think about what it's possibly suggesting can happen. What this is suggesting is you might have an integral. And you're trying to integrate the product of two things. What this formula says is, suppose that integral's challenging. If you recognize the functions you're trying to integrate as a function times the derivative of another function, it's possible that you might be able to take your integral on the left-hand side, which you're unfamiliar with or challenged by, and you might be able to write it as something minus an easier integral. So again, the way I would like you to think about it is as follows. So in many cases, or I shouldn't say many cases, so it's helpful to think about this. So I write down, we had f times g prime dx equals f times g minus the integral of, I'm going to rewrite it slightly. I'll write it as g times f prime dx. And the way I would encourage you to think about it is like this. Hard integral equals something, which we don't have to integrate, minus, hopefully, easier integral. So again, what this formula allows you to do is it allows you to take an integral, possibly one you can't do, and express it in terms of an integral you can do. So there's a pretty standard way of learning this integral formula and applying it. So to make the formula easier to use and hence memorize, we often do the following. So we often set u equal to f of x. And we often set v equal to g of x. And when you do that, what that tells you is du is f prime of x dx. We use our differential notation. And dv is g prime of x dx. And so if we write the formula down, we can write it down in a more compact way. So the original formula was the integral of f times g prime dx is equal to f times g minus the integral of g times f prime dx. And if you replace these symbols with the corresponding u's and v's, you can write this in an easier way to memorize. It's u dv equals uv minus the integral of v du. And this is typically how it's stated in books. And this is a little easier to memorize. Plus, when you think of it in this way, it kind of gives you a more recipe for how to use it. Does anybody have a question? We're about to do some examples, and hopefully it'll help clarify some of the concerns. But if you have a question, please ask. Okay, well, let's see how we can use it then. So the first example that we're going to ask is what's the integral of x times the cosine of x dx? So a good procedure for kind of learning how to do this is you want to choose a u and then you choose a dv. So that's what we're going to do. So what I recognize when I look at this is I have two functions in there. Both the function x and the function cosine of x are easy to differentiate. They're both easy enough on their own to integrate. However, what we recognize is the derivative of x becomes a quote-unquote simpler function. It becomes something that is, it becomes constant. Whereas if I differentiate cosine, what happens is it goes to the derivative of cosine is negative the sine. Then you differentiate it again. You bounce back from sines and cosines over and over again, and it doesn't make it any quote-unquote easier. So what I'm going to do is I'm going to choose my u to be x, and I'm going to choose my dv to be cosine x dx. And then next, I'm going to compute. What's du dx? Well, we get right away that du dx is equal to 1. And what is v? Well, how do I recover v? If I know the derivative of something, I'm looking for a function whose derivative is cosine. Well, that tells us right away that v has to be the sine. So again, the first thing I do is I choose a u and I choose a dv. And then I say to myself, okay, if this is my u, what's my derivative, my du dx? So of course, we often just write this as du equals dx. We use our differential notation. So we make this choice, and now what we'd like to do is we'd like to apply this formula to these specific values for u and v. So if I flip the page, I'm going to write this down in a little very carefully. So the integral I was interested in was x cosine of x dx. And we know that that is uv minus the integral of v du. And let's not forget what our u and our v was. So this was our dv, and this was our u. So this becomes x, and then our v was sine of x, and then we're left with the integral of v, which is sine of x. And then what's du? Du we found was just dx. And what we would really hope happens is exactly what happened here. We took an integral that was unfamiliar to us, x cosine, and we used this formula to express it as a function minus an integral we can easily compute. So before I finish this, there's one step left. Does anybody have a question? Does anybody have a comment? Okay, so if no one has a comment, we'll finish this problem. The integral of sine is negative the cosine. Then, of course, we have our plus c because these are indefinite integrals. And we arrive at the final or solution, if it were. So does anybody have a question about this? Again, the theme here is we took an integral we weren't familiar with, and we expressed it in terms of an integral we could compute. Okay, let's do another one. We'll go a little faster this time. Suppose now we want to integrate x times e to the 5x dx. So here's what my thought process is. My thought process is, once again, I have the product of two functions in there. I have x, and then I have e to the 5x. And so what that means to me is that since it's a product, it's a good chance that the integration by parts formula will help, because that's involving products. And I also see a function that's easy to differentiate, and that makes me think that parts will be a good choice. So what I do is I say, okay, let me make some preliminary observations. I'm going to set u equal to x, and I'm going to set dv equal to e to the 5x dx. And once again, that means my du is just dx. And my v is a very simple integral. It's just 1/5 e to the 5x. So the question students have is, how do you know to choose for u? How do you know what to choose for dv? The simple answer to that is you don't until you have experience. Experience, experience, experience. So once again, I know this integral is equal to uv minus the integral v du. So I'm left with 1/5 x e to the 5x minus 1/5 the integral e to the 5x dx. And the parts formula has given me what I really wanted to happen. I have a new integral which I can readily evaluate. So when I integrate this, I get 1/5 and then times 1/5 e to the 5x plus my constant c. And then if I wanted, I can clean this up. If I factor out a 1/5 e to the 5x, then this is just x minus a fifth left, and then of course plus c. So these are standard examples. You should practice them until you can do them. Any questions, comments? So sometimes you have to perform this sort of more than once. So let's look at another example. Let's integrate this time, say x squared e to the x dx. This guy will require two integration by parts. Oops. So the first thing I'm going to do is I am going to let my u equal x squared, and now my du becomes 2x dx. And then if my dv is e to the x dx, my v is just e to the x. And when I apply the formula the first time, I get uv, so I get x squared e to the x, minus the integral of v du. So what that becomes is that becomes 2 times the integral x e to the x dx. And so now we're left with an integral very similar to the problem we just did. And in order to integrate this guy, we have to use parts again. So now I'm going to let my my u is going to be x. So my du is just dx. And my dv is e to the x dx. And I'm left with v equals e to the x. And so now this is how my brain's going to want to do it. I'm left with x squared e to the x minus 2. And in here, I'm going to be very, very careful. That integral, just so I don't mess anything up, I'm going to write down what it is. It's my new uv. So it's uv minus the integral v du. But I have to make sure I use my correct u and v. I'm using the second u in the second dv. So the uv now is x e to the x. And then this is minus integral e to the x dx. And so carefully, I'll compute the last integral, which is just e to the x, plus c. And then I can clean all this up. And there is the answer. It's often easier if you want to sort of clean it up if you can. I can factor an e to the x out of everything, and you're left with e to the x minus the polynomial. X squared minus 2x plus 2. And then, of course, we have our plus c. Does anybody have a question, comment? Is everybody sleeping? Yay, it's Thursday. It's a good day to sleep. All right. So, let's move on. All right, any questions, comments, concerns? All right, so let's do a fourth and final example. Let's integrate the natural log of x dx. So this integral usually baffles us the first time we see it, because you'll say, how can you use parts if there's only one function there? But there's really not just one function there. There is the log, but it's also, you can imagine that you're multiplying the log by 1. So there's another function there, 1. And so with that in mind, it seems reasonable to try this. U equals the log of x, and then dv is just dx. And so your du is 1 over x dx, and your v is just x. And with that happening, you get uv, so it's log of x times x minus the integral of v du, which is x times 1 over x dx. And if we write this a little more appropriately, we get x log x minus the integral of 1 dx. Which becomes x log x minus x plus c. So you now know the antiderivative of the log function, or the integral of the log. All right, any questions about this? Comments? All right, great. So there's lots more examples we can do, but it's often best that you learn these on your own. And so we'll let you do that with the next homework assignment. All right. Okay. All right, so what's our next technique we're going to study? Our next technique is I'm going to put technique in quotations because it's not really a technique as much as it is recalling some old facts. So what we want to deal with powers of sine and cosine. So that's kind of where we're going to start. So here's the theme. Is the power even or odd? So the most important thing you need to ponder is what is the power? So for even powers, so this sort of the idea or the trick is to use what we call the half angle formulas. So you might remember what these are, you might not. For example, the cosine squared of an angle is 1/2 times the quantity 1 plus the cosine of 2 of that angle. And then there's a very similar formula for sine. The only difference is there's a minus sign here. Both formulas have cosine in them. So these are the half angle formulas you learn about you should have learned about in a trig class, pre-calculus course, somewhere along the line. Okay, so let's do an example where that's the case. So start with a baby one. Suppose we want to integrate say cosine to the fourth. Well, what we'll do is we'll start by recognizing that this is the same thing as cosine squared x times cosine squared x. And of course, using our half angle formulas, cosine squared just becomes 1/2 times 1 plus cosine 2x, and then times 1/2 times 1 plus cosine of 2x. Which of course will pull the 1/4 out, and then if you multiply your 1 plus 2 cosine of 2x plus cosine squared of 2x dx. So if you do that trig and that algebra correctly, what you're left with is you're left with 3 terms in your integral. The first 2 are straightforward integrals. The third one is not yet, but we can apply the same rationale and use the double angle formula again. What I mean by that is this is 1 plus 2 cosine of 2x. By the double angle formula, this becomes 1/2, 1 plus the cosine. It's not of 2 anymore, it's now of 4x. And so if we combine our like terms, 1/2 is 3/2. And so we now have 3 terms which we can integrate. What does this equal? It's 1/4. The integral of the first guy is 3/2 x. The integral of the second is sine of 2x. And then the integral of the third is plus 1/8 of the sine of 4x. And then, of course, you have your plus c. Now, you can multiply the 1/4 through, I guess, if you wanted. So you could see these integrals are pretty tedious. And the larger the power, the more tedious this creature is going to become. Does anybody have a question about this? All right. Turns out the even ones are a little more tricky. I shouldn't say tricky, but they're more algebra ridden than if it's odd. So let's look at an odd situation. So for odd powers, what we're going to use is we're going to use the Pythagorean identity. Sine squared plus cosine squared equals 1. So here's how you can go about doing that. So let's say, for example, we want to integrate the 5th power of cosine. So the observation or the trick is to break it into an even power times the power 1. So you'll notice that I'm writing the 5th power as 4 plus 1. This is just elementary exponent properties. And now the next observation I'm going to make is that cosine to the 4th is nothing more than cosine squared, quantity squared. And so using the Pythagorean identity, I can replace this cosine squared with 1 minus sine squared, which at first glance, it looks like I'm making things worse. You might say, well, it looks like you're kind of complicating things. But that's only if you look at it from one perspective. If you look at it from another perspective, you might say, oh my God, this is an extremely simple integral. Because there's an obvious substitution that is staring you in the face. So what do I mean by an obvious substitution? Well, it might not be obvious to you right now, but what I'm going to recognize is that if I choose u equal to sine of x, and then my du would be cosine x dx, this integral reduces to a beautiful polynomial upon the substitution. This becomes 1 minus u squared, quantity squared du, which of course is a polynomial. It's 1 minus 2u squared plus u to the 4th. Which is very easy to integrate because it's just u minus 2/3 u cubed plus 1/5 u to the 5th plus c. And then all that remains to finish the problem is to plug the x's back in. And so we'll do that on the next page. While I think about that, though, does anybody have a question? Does anybody want to point something out? Let's remind ourselves that no one said that this was going to be easy. Integration is by nature challenging.
Professor?
Yes.
So we went from the cosine squared x to the 1 minus sine squared x using the half angle formula?
No. You talking about in this problem?
Yeah, right there.
No, I got, if you're worried about how I got this right here, this 1 minus sine squared, I'm using this. Take sine squared and take it to the other side of the equation. What is cosine squared equal to? It's 1 minus sine squared. So
okay.
I'm using this equation to go from here to here. So I put star here. How did I get this? This is from star.
Got it. Thank you.
Yep. Yeah, so this is, again, no one's pretending this is easy. It's going to take a lot of effort for you to learn this. It's just what it is. I wish there was a simple solution. I wish I could say, hey, guys, this is so easy, but it ain't. It's quite a challenge to learn this stuff. So you can give up and say, that sucks. The world is stupid. Why do I have to learn this? Or you can just accept the challenge and learn it. Like the millions who come before you have done. And the millions who will come in. Okay, so we have to put the final bow on this. So if we go to the next page, we can write our final answer. The integral of cosine to the fifth, which we started with, is no, I already forgot. What was it? U. So it's sine x. Yeah. So it's sine x minus 2/3 sine cubed, and then plus 1/5 sine to the fifth plus c. That was fun. That was so fun. All right, any questions about this? Okay, so here's the next thing. For products, we play the same game. If at least if at least one power is odd, use this formula. So let's do an example to illustrate what I mean. So all you have to do is, if both are even, you're going to use the half angle formulas. But as long as one is odd, you're going to use this Pythagorean identity. So let's look at an example to illustrate. So a good example would be something like, how about sine cubed x cosine to the negative 2x dx. So I have two exponents. I have a 3 and a negative 2, and I see one odd. So what I'm going to do is I'm going to do the same strategy I did in the previous problem. I'm going to break the odd guy up. So I'm going to have sine squared x times cosine to the negative 2x. And then I have an extra sign floating around. So I'm going to put it right here. Now, why am I putting the sign there? Because I already know what's going to happen. I've done these for years. I understand how this works. So what I'm trying to convince you of is if you do enough practice, you'll see why I'm doing things the way I'm doing. All right, now, the next thing for me to do, and I'll pick on you, Tom, because this is the same thing. Notice this sine squared. I'm going to replace it. I'm going to replace it with 1 minus cosine squared. So that is what I mean by using the Pythagorean identity. Because now, what I have now is I have a great setup. If I choose u equals cosine, and then du becomes negative the sine of x dx, my integral simplifies to a polynomial. Well, I shouldn't say a polynomial. It simplifies to a very simple algebraic expression. Because this is going to become minus the integral of 1 minus u squared times u to the negative 2 du. Where that minus sign comes from my derivative, du is minus the sign. And so I can distribute this u to the minus 2. So I'm with u to the minus 2 minus 1 du, which of course simplifies to the integral 1 minus u to the negative 2 du, which is u, add 1 and divide by it, so I get plus 1 over u plus c. And so your final, the answer, as you guys always like to say, becomes cosine of x plus 1 over cosine, which is just secant, plus c. Yikes. Does anybody have a question?
Yeah, Professor.
Yes, I'm listening.
Yeah, where's that in the line 1 minus u squared times u to the negative 2? How do we end up with just 1 u to the negative 2?
How did you end up with just 1? What do you mean?
Well, it went from there's
the cosine was raised to the negative 2, but I'm replacing cosine with u.
Right. I guess this is more of an algebra question then. We went from the 1 minus u squared times
Are you talking about how I went from this line to this line?
Right.
Yeah, so distribute. So if I take u to the minus 2, I have to multiply it by here. That gives me u to the minus 2. And then when I multiply it by here, I get u to the 0, which is just 1. So when you do your exponents, what is 2 minus 2 is 0. So you get u to the 0, which is, I mean, if you wanted to, you could think about it like this. I could have written this as u to the 0, but that's just 1. And so why did I flip them in the next line? You might say, well, how did I get this? Well, then I distributed this negative sign back through. So again, you can go different ways of this and it still be correct. That's just the way that I chose to go about it. I pulled my negative all the way out until it was safe for me to put it back in, because I didn't want to make any errors. So again, what I'm doing from this line to this line is I'm just doing algebra. Once again, let me reiterate, this is not easy. This is challenging stuff. It takes, it's funny, you guys are going to hate to hear this. But I was reading this article the other day and they were talking about, learning science and math. And the author of the article said something to the effect, if you're reading a page in a math book in less than an hour, you're not learning anything. So the point being, a problem like this, understanding this is not 5 minutes of your time. Trying to understand these problems, this is hours of your time. And that's one of the things I mentioned to you guys before, and I guess I should mention it again. Maybe it'll make you mad, maybe it won't, I don't know. But, in my opinion, and this is the opinion of a lot of people, learning science, being a science major, and learning math, particularly things like calculus, it's not how smart you are. Of course that helps. Being smart helps, just like being fast helps in sports. Being strong helps in sports. Of course that helps. But it's not about how smart you are. What it's really about is it's about how willing are you to sacrifice your time. Because learning this stuff and learning organic chemistry or learning biochemistry or learning how to program or write software, that is time consuming. Nobody learns it overnight. It is just experience piled on top of experience, piled on top of experience. And what's overwhelming and what makes that challenging, particularly in something like calculus, is the language is often not English. This is a whole new language. It's symbols. It's overwhelming. Many of us are intimidated by what it looks like, and so we sort of don't even attempt to learn it because we're so overwhelmed by it. But you got to somehow dig deep and say, you know what? Who cares? I'm going to learn this, no matter what it takes. But you know, you can't expect that by 8 o'clock tonight you're going to understand integration by parts and you understand trigonometric integrals. You're just not. It's going to take hours of your time to be able to do this, and even then you're going to be like, I don't understand what's happening. That's just the trials and tribulations of it. It's the process of learning. Anyhow, again, I don't say that to overwhelm you guys. I don't say that to make you think about becoming a basket weaving major, because you'll suck at basket weaving too if you don't do it all the time. It's like anything else. You want to be a good writer, you got to write all the time. Anyhow, I think this is probably a good place to stop so that you guys can actually start working on these things. I see a question coming in. Yes. Very good, Paul. Very good. But you didn't see sine squared times cosine squared. You saw sine squared plus cosine squared. That's a good joke, by the way. I do. Oh, I see what you're saying. Never mind. I get it. Okay. Does anybody have a question? Took me a minute, Paul. Took me a minute. All right. Well, listen, if you guys don't have questions, I will post your next assignment. I would encourage you to please email me with questions. And if you need help or whatever, I'll be willing and able to do it. And otherwise, I will see you guys hopefully Tuesday. All right, guys. Thanks for joining in, and good luck learning. Enjoy it. Don't make it miserable. Make it fun. Have a great weekend. Take care, guys.